All right, so today we're going to just talk about a brief preview of calculus. We're going to just look at a few concepts, some things about, generally speaking, what calculus is, and that's actually where we're going to start. So the idea first about calculus, what is calculus? And there's lots of things that we could sort of say as a description. The description that I want you to think about is what calculus really is it's the mathematics of change. Calculus is studying how things change. And we do that in a variety of ways with a variety of very technical math, manipulatives. But that's what calculus is. It's studying how things change. One of the ideas to study how things change is to talk about a secant line or a tangent line. So a secant line is a line that goes between 2 points on a shape. And then a tangent line is a line that only touches the shape at one place. So those are two ideas of how calculus kind of starts. So where have you seen, if you've had calculus before, I don't mean in calculus when I was in high school, where else have you seen the phrases secant and tangent used? There's two other places that are common, people have seen them. Geometry and trig. And they're kind of used in a different way in each of those classes. So we're going to think about it from a geometry standpoint for the moment, okay? So a secant line in a geometry standpoint is a line that crosses through an image, something like this. There's no real specifics on how it has to cross. There's just 2 points and it crosses through them. And it really doesn't have to be a circle, although that's what you looked at when you were in geometry. It can be any shape. So it can be like this too. However, a tangent line doesn't do that. A tangent line simply touches the curve or the shape that you're dealing with. I've had students refer to it as it kisses it before. That's a really good image. It's very surface is what we're talking about. So when you have something that's tangent, it looks like this. This would be considered a tangent line to my circle. And you can do the same thing over here with our other image. This would be a tangent line, at least visually it would appear to be, for this cubic graph. So these two concepts will come up in calculus as we start moving into derivatives in Chapter 2. There's another couple of examples using calculus that are dependent on numerical methods. Like we can do them approximating, we can find things using numbers. So the next one I'm going to take a look at is we're going to calculate the slope of something. Now, if you've had calculus before, you may sort of recognize this as something you've seen. Hey, I've calculated slope before, and it's probably not going to look like what I'm about to show you. But from a very numerical standpoint, we can calculate slope by using a slope equation. So, time to pull on like the algebra stuff that you remember from, I don't know, it may have been quite a while ago. Do you remember what the formula is for slope? Okay, that is a formula that has slope in it, but it's called the the slope-intercept form of a line. So that's actually that's actually the formula or the equation for a line, not for slope.
Is it y minus y sub 1 equals m times x minus x sub 1?
Yeah, so we usually would say like m equals, and you can do y1 or y2 first, it doesn't matter, but whichever one you do first, the denominator is the same underneath. So if you choose to do y1 first, then it needs to be x1 first underneath. Do you guys remember that formula? You should have seen it several times through your math in high school and probably even a little bit in middle school. Formula for slope. So what we're going to do is we're going to calculate the slope, but the problem is we're calculating it at one specific point. Normally when you calculate slope, and even if you take a look at this equation, what do you need? 2 points, right? And I don't have 2 points, I have 1 point, and that's a problem. So we are going to have to figure out what other point I'm going to use in order for that to make sense. So what we're going to do is we're going to do two things. The first thing, the first thing before we even get started is this a equals 1. Is a an x value or a y value? Like, is it going to be the x1 or the y1? Yeah, it's an x value. So the first thing I'm really going to need is I'm going to need to know what's the y value that goes with it. How do I do that? You plug it in usually, so we don't have to necessarily graph. You can see it from a graph, but you can also plug it into the equation. So we can plug in f of 1, because our a value is 1. So this would be 1 cubed plus 2, which would be a grand total of 3. So our first x1, y1 pair, if you will, is that we have 1, 3. That is going to be one of our points that we're using in this point slope form. So what we're going to do next, though, is we need to pick another point. Now, in general, you could pick anything, but of course, the answer is going to be different based on what you pick, right? If I pick a different x value than you pick for my other point, I'm going to get a different slope. So for the time being, we're all going to pick the same x values, and I'm going to lead you down the path of the idea of what this is doing. The first x value I'm going to pick is 1.1. I want something very close to 1. My goal is to get the tangent line, right? The slope of the tangent line. I don't really want the slope of a secant line, right? The image over here, if I have these 2 points right here, and I calculate the slope through them, that doesn't give me the slope of a tangent line. It gives me the slope of a secant line. But if the 2 points are really, really, really close together, it starts to look a lot like a tangent line, doesn't it? So what we're going to do is we're going to pick a point that's really, really, really close. In this particular case, we're going to pick 1.1. So let's do it again, but let's get a little bit closer even yet. And I'm going to pick 1.01. That's even closer to 1, isn't it? What do you think my last point might be for this table? Yeah, 1.001. Just, it's a pattern, that's all it is. And there's nothing special about these points except that they get very, very close to 1, and they are closer than the one before. Okay? So grab your calculator out. If you have it with you, if you don't, I'll let you use your phone for today only. Okay? Grab your calculator if you have it. And if you do have a TI 84, 83 with you, I'm going to show you a few tricks as we work today that will hopefully help you when you do your homework. So what I'd like for you to do, if you do have your TI calculator, is I'd like for you to hit the table set button. That's second, and then window. You get a picture that looks something like this. Hit the yellow or green or whatever it is on your calculator top corner, second button, and then hit window. The important part of this menu right here is not what it starts at. That doesn't matter at all. It's that right here where it says auto and ask, the first one says ask, and the second one says auto. By the first one saying ask, it will allow you to put in a value into the table so that it will allow you to pick what you want it to calculate instead of automatically picking it for you. Okay, so everyone who has that kind of calculator, are we good so far on that piece? Here's why this is helpful. If you will hit y equals, clear out whatever you have in there, and put in this equation, which I recognize this is not a particularly complicated equation. We could do this by hand, and those of you who have a phone can certainly do this by hand today. But our equation is x cubed plus 2, right? If I do this, then I can go into the table, which is second graph, delete out what I have, and I can put in those 3 values that I just picked, 1.1, 1.01, and 1.001. And my calculator did all of the work to tell me what those numbers are. And I did it like this, which is really cool. So these are the first things I'm going to write down, is I'm going to write down the corresponding y value. So the first one is 3.331. And you can tell on the bottom of the screen right here that that's complete. It doesn't have any more digits to the right. It is 3.331. Your book wants you to record things accurate to 6 decimal places, which I know sounds like so many, but your calculator is doing all the work. So here's the second one. This one actually has 6 decimal places. So we have 3.030301. Then we have one more, and I think it has more than 6. It does. So we will just write the first 6 of these. The first 6 of these is 3.003003. Now what do you notice about these y values? What's happening as we go down the list? They get closer to 3. And we kind of should think that makes sense because the actual y value that we have when we plug in the number 1 actually was 3, right? So if my x values are getting closer to 1, it makes sense that my y values would be getting closer to 3. Now, that doesn't always happen on every function, but on continuous functions, which this one is, that's a typical behavior. Okay, taking our calculator screen over, or our computer screen over here, we're going to calculate the slope, just not yet. I want to calculate or show you what to do with the other x values. Notice, what can you tell me is the same about all three of the numbers I picked compared to the number 1? Can you tell me something that's the same about all those three numbers compared to the number 1? They're higher. They're all greater than 1. So this is sort of looking just to the numbers that are on the right side of the number 1, right? They're all bigger. Well, that's sort of a lopsided view. If I'm only looking at the values that are bigger, I might get some information that's not quite what I was expecting, right? It really might not be accurate. So I don't need to just go to the right of 1. I also need to look to the left of 1. So something slightly smaller than 1 might be the number 0.9. Any idea what the next one might be? Somebody said it. It's 0.99. What might my last one be? Yeah, 0.999. These numbers are getting, again, closer and closer to the number 1, but this time they're all slightly smaller than 1. And because I've got this cool thing my calculator can do, I can put all of these into my calculator, and it takes me about 3 seconds, and there they are. And I can go back up and I can actually look at the values and write them into my table. So the first number is 2.729. That's definitely the furthest away from 3. Almost as far, well, about as far away from 3 as the 3.331. We're really, looking fairly far away from 3 at that point. But the next one gets awfully close. 2.97. 0299. 6 decimals when you can, when there are 6. Oh goodness, and the last one, lots more than 6, so we'll just write down 6 of them. 2.997003. And if you write 002 and don't round that last decimal, that's really okay. It's not going to affect anything that far out, but it is a 3 if we round. Okay, is everybody good so far? Okay, what I want you to do next is go out into the regular screen of your calculator, just the plain old regular screen. And what we're going to do on my screen over here where I'm writing is we're going to write down the first slope that we're going to calculate. In particular, we need to subtract y values on top, x values on bottom. We know that one of the y values we're going to use is 3. So what I'm going to do is I'm going to write down minus 3. And we're going to use the very first y value in my table otherwise. So in my table, it's 3.331. So we've got 3.331 minus 3. I'm going to put this in parentheses. And I'm going to put a division sign. I'm actually writing down the way it will enter into my calculator directly in just a moment. And then I need to make sure I subtract my x values in the right order. What's the x value that goes with 3.331? 1.1. What is the x value that goes with 3? That's 1. So the order matters. We have to make sure the orders match. And then you can use your calculator to put this in. So I'm starting with a parenthesis. I'm going to do 3.331 minus 3. Close my parenthesis. Division. Make sure you open the parenthesis on the second half. 1.1 minus 1. And close it. I'm going to hit enter, and this will give me the slope between the 2 points, one at x equals 1 and x equals 1.1. So the first slope is actually 3.31. Now, it happens to be a number close to 3. That's just what happened to happen. That certainly does not always happen, that it matches sort of what looks like the y value. That's just the function that we're using, okay? We're going to do the next one, but here's the cool thing. Because I already have my calculator with this already in here, I mean, the next one's going to have different numbers, but the numbers 3 and 1 are going to stay the same, right? I'm not going to change those. So like in particular, what I'm about to enter is 3.030301 minus 3. divided by, and now I'm going to enter 1.01 minus 1. I'm going to go ahead and do that by hand, and then I'm going to show you a shortcut here in a second. 3.030301 minus 3 divided by 1.01 minus 1. And we're going to hit enter. And I happen to get, again, another value that looks a lot like the y value I had to begin with. That's just happenstance with this particular problem. And I could keep entering all these by hand. It would take me a little bit of time to do, but it wouldn't be terrible. But here's something really cool. If you're using the TI, you can hit the second button, and do you see how it looks like I've got a little T or a little cross right there blinking now? That's how I hit the second button. That's what it does. And then you can hit the enter button in the bottom right-hand corner, and it brings up the last entry that you used. So I can go in and I can just change what my entry is. I don't want 3.030301. I want 3.003003, and I just type right over it. And then over here, I don't want 1.01, I want 1.001. Now that's a little trickier because I don't have enough spaces right now. Well, there's a way to get spaces in there. You hit the second button and the delete button, and then it becomes an insert button. Second delete is insert. Who knew? And so I can enter another 0 in there because the number I'm supposed to be using now is 1.001 minus the 1. And this becomes 3.003. I know I'm showing you guys a lot of calculator tricks. I mean, that's really what it is. It's uses of the calculator in a creative and simple, a way that makes your life simpler once you know the tricks. I don't want to overwhelm you with this. You can do this all by hand. But if you get some of the tricks down, it'll save you time. The Success Center, my office, if you're not catching all my tricks, that's cool. Come and ask me because I'm happy to show you again multiple times, however long it takes, so that you have those at your disposal and you're able to use them. We're not going to use them substantially throughout the course, but when they come up, it's really nice to have them sort of in our toolbox of things I can do. We're going to do the next set over here as well. I'll write the first one down. I'm not going to write all of them down, but because we're going to do them in the calculator anyway. I'm going to keep the numbers the same direction, so I'm going to do 0.9 as my first number. I'm sorry, not 0.9, the 2.729 minus my 3, just like I did before. Y is on top. And then my x value, which was the 0.9, minus my 1 on bottom. Now from my calculator screen, I can go in and I can change what's here. I did second, enter, and it brings up my last line of text. And I can go in here and I can change it. I'm going to do 2.729, and because I know I'm going to want those placeholders later, I'm just going to put zeros there for now to save the placeholders, okay? And it's supposed to be minus 3, so that's good. And then I need 0.9, and again, I know I'm going to want some placeholders here, so I'm just going to zero everything out for now so that I have the space there and don't have to do the insert key again, and I'm going to press enter. And this one's the slope that I just calculated is 2.71. We're going to do it 2 more times. Here's my screen. I'm going to do second enter. I'm going to change it to the second y value in this particular table, half of the table I'm looking in, which is 2.970299. I used all 6 buttons or 6 placeholders on this one, minus my 3. And then it's 0.99 minus the 1. And I'm going to hit enter. It's going to give me 2.9701. We're going to do one more time, second enter. I've got 2.997003, or some of you had probably written down 2, which is fine. And then I've got 0.999. I actually don't need that last 0, or I could leave it either way. Minus 1. And this is 2.997. Now, if you go back up and look at the directions real quick, we've filled in this table. Okay, we did. We filled in all the table. But the directions actually didn't say fill in the table, did it? And we have to fill in the table, don't get me wrong. But that's not what the directions said. The directions said to estimate the slope. So we have 6 slopes on our screen right now. 3.31, 3.0301, and so forth. We've got 6 different slope values. What we're looking for is as we go down the table, right, as the x and y values got closer and closer to our x and y value that we care about, x equals 1, y equals 3, what is our slope doing? In particular, so in particular, as I go down this table on the slope columns and down this on the slope columns, what slope value does it appear, and this is an estimate because that's all we can do with numerical techniques, what does it appear that my slope is getting close to? 3, which happens to be the y value, but that's, again, that's just the way this particular problem was worked out. So our slope is approximately 3. Now, in reality, it's exactly 3. That's actually the exact value. But we can't make that claim yet. We haven't proven that or actually done that with any calculus and tens techniques. This is just a numerical approximation. I know that this is tedious, but are we kind of okay with it at the moment? Have the basic idea what's going on? Okay, great. All right, let's see what's going on next. We're going to do the same thing, but we're doing it with a trig function, tangent. Now, one thing I want you to be careful of, and I throw this in here immediately because I need to make sure you notice it in class and not in your homework by accident later, is that your mode in your calculator, when you hit mode, needs to be in radians. So if it is not currently in radians, please change it. You will never do calculus with degrees. It'll always be in radians, okay? So make sure your mode says radians. That's one of our issues. All right, our next issue is that this one isn't quite so clean in terms of my a value. My a says pi over 4, which is a great value for a trig function, like pi over 4. It's not such a good value for saying, oh, I'm just going to go 0.1 higher and 0.1 lower. I mean, I want 0.1 higher than pi over 4. It sounds a little awkward. So one of the things that we're going to do here right at the beginning is we're just going to get an approximation for pi over 4 because, oops, I did pi over 3. Let me try that again. Because it might help us to think about what that decimal expansion is as we're approximating it. So just to keeping in mind, I'm looking at a number that's about 0.785, roughly, and that's our first 3 decimals. If you want to write a few more down, you certainly can. But that's the value that I'm trying to get close to, is my idea. In fact, you know what, I am going to write down a few more because I'm going to leave my screen here in a minute. I might want them. 39816. Okay. All right, so just like last time, I need a table. Now, when you're doing your homework, it's not going to actually show you a table. You're going to have to know, I'm supposed to create a table when it asks me to do this. So when it says estimate the slope, what it's asking you to do is to create a table. Your table is going to have 2 components, just like mine does. One half of the table, or one of the 2 tables, if you think about it that way, is going to be values bigger than the x value. The other is going to be values smaller. Okay, that's always going to happen. So let's go ahead and start with values bigger, just because that's what I did last time. What is a value bigger than 0.7853, whatever? Slightly bigger, not a ton bigger, but bigger. Anyone? 0.8. That sounds great. We'll do 0.8. Agreed? It's bigger, but not a lot bigger, right? Sure. How about a value that's closer than 0.8, but still bigger? 7.9 would be okay? That'd be all right. We're going to do it again. A value that's close to 0.785, but bigger. 7.86 would be a good choice. So there's actually nothing specific about these numbers. Actually, I don't think these are the numbers that are on my paper for my note sheet even. But it doesn't matter. The point is that the numbers are getting closer to what you want, but they're all bigger. Okay? So while we're here, let's go ahead and pick our other x values, because we can. We want numbers that are slightly smaller than the number I've got. So what do you think what could we start with? 0.7. Sure, we could start with 0.7. What might we do next? The smaller ones are actually really easy on this one. 0.78. What might we do for the next one? 785. This one's really cool because you just sort of like knock off the rest of the decimals and it's automatically smaller. Yeah, so I kind of like doing it that way, 785. All right, so what we're going to need next is we're going to need the y values that go with these values. So if you'll remember what we did before, we actually took our table and we, in y equals, wrote our function. So our function is tangent of x. So tangent x, and we're in radians, so we're good with that. And in our table, we're going to put in all these values. Now, we actually haven't done one of the other things too. We haven't actually found out what is the tangent of pi over 4. Do you remember what the tangent of pi over 4 is from trig? Radical 2 over 2. I hear 1. I hear some more people saying 1. Both of those are numbers on the unit circle for tangent. You're right.
Tangent isn't sine over cosine?
Right. Tangent is sine over cosine. Yeah. So it is a value of 1. Yeah. So the tangent value is actually the value 1 when we're plugging in pi over 4. So our y value, when we plug in pi over 4 on this actually, is the number 1. So our ordered pair that we're going to be referencing is pi over 4, 1. Now we're going to use our calculator for all the rest of them, because they're definitely not unit circle values. So we've got 0.8, 0.79, and 0.786. And we're going to plug those numbers in, and we're going to go over and we're going to write them down. So I have 1.029, 639. 1.009246, and 1.001204. What can you tell me about those y values? They're getting closer to 1. And is that a reasonable thing to think would happen? Yes. Does it always happen? No, but it is reasonable that that would be happening. All right, we're going to do the other three. So I have 0.7, 0.78, and 0.785. And we're going to do the same thing over here. 0.84, 22, 88. 0.989262 and 0.999204. Again, getting closer to the value of 1, right, as we go down the list. All right, so what we're going to do over here then is we're going to do the slope. So when we calculate slope, we're going to take the first y value, and I'm going to actually use just the first f of x value in my list, 1.029639, minus my first actual y value for my point that I'm actually caring about, which was the y value of 1 at the top of our screen. And then we're going to divide that by the x value that we care about. Now, it's actually 0.8. But just for being able to enter my stuff in my calculator in a moment, I'm going to put 2 more zeros on there so that I don't have to worry about that, second enter button or second delete button to insert things. And then I'm going to do minus, and I'm really going to put in minus pi over 4. I'm not going to write in the approximation for it. I do want it as precise as I can. So back in my calculator, I've got 1.029639 minus 1 divided by 0.8 minus pi over 4. And the first slope value that I calculated was 2.029813. And we're going to keep doing this. We're going to go down to the second one. We're going to change the entry value, the values that we're entering. So the second one is 1.009246 minus 1. And it's now 0.79 minus pi over 4. This is 2.009198. Again, round the last digit or don't, it really doesn't matter. And the last one in this column is 1.001204 minus 1, and it's 0.786 minus pi over 4. And now I have 2.000543. The other half of my table, value is slightly smaller. I don't have 1 point something. I have 0.842288 minus 1 and 0.7. So I'll just zero out the other two digits for the moment, minus my pi over 4. So this is 1.846784. Okay, we'll do one more. 989262 and 78. So I have 1.989195. And then my last one is 999204. And then minus 785 is the other digits. And I have 1.999179. Are we done? No, because we didn't answer the question yet, right? Are we required to do the tables? Yes, in this section, this is exactly what we're doing. So we've done what you needed to do so far, we're just not finished. So what is this showing us as we look down the slope columns in both sides of this table that we think or can approximate our slope to be? The slope appears to be 2. And again, it's not just an appears, but all we can do right now is say that that's the estimate that we're getting. Okay? I know that we only have about 5 minutes left. We are going to keep going. We're not going to get finished. The good thing is that since we're not going to get finished, what do you think that means? The homework's not assigned. So that's really nice. That doesn't always happen on my first day. So we're going to continue to the next slide, but we won't finish it. We'll finish up next time. Let me take a look with you on what's going on. All right, so one of the things that we've estimated so far is we've estimated slope, right? Slope is a really important concept in trig, or in calculus. We're going to see it happen and come up again and again and again. Another one that we are going to estimate using this numerical technique is we're going to estimate a length of a curve. And we're going to do it based on having 4-line segments and 8-line segments in a moment. We'll do the 8-line segments next time, but we will at least start with our 4-line segment idea before we leave. So what are we doing? Well, we've got this function, f of x equals the square root of x plus 1. And if we were to graph it, and I'm going to not graph it at the moment, but you can if you would like, it looks something like this. Again, I didn't put any axes there, but it's got this kind of a shape to it, general shape. So if I want to estimate the length of it, obviously I can't do that with a ruler because it's curved, right? So what do I do? Well, wherever our starting point is, and we'll just say image-wise that it looks like this, our starting and our ending point, I'm going to break it apart into segments, equal segments. So if you're thinking about like your xy axis down here, if this point started at, what's my number here, 0, and it ended at 3, and we want to break it into 4 pieces, we're going to break it in half. What's that halfway point? 1.5. And then we're going to break it in halves again. So what would be those other halfway points?
0.75.
All right. 0.75 on the first one, and what's the third one? 2.25. You have filled in, I mean not physically, but you have written down now all of the values that go in the x column. The first number is the first endpoint, 0. The last number is the last endpoint, 3. Halfway between was 1.5. Halfway between that was 0.75. And halfway between that was 2.25. Easy enough. Now visually, and this is where we will pause for the moment, visually what we've done is we've said, here are the points that go with these, and again, my graph doesn't look very nice and tidy, but if these were the points that go with them, what we're physically going to do is we're going to put line segments between each of these dots. Now, do the line segments give you the exact length of the curve? No. But do they do better than taking the first point and the last point and using that as your line segment? Yeah, it's better. So what do you suppose is going to happen when I use 8 line segments? Is it going to get better or worse? Better. With few exceptions, it's going to get better the more line segments we use. So this is what we'll do next time. We'll calculate the length of this curve, both this one and then with the 8 line segments, and then we'll move on into section 1.2.